Welcome to you all from Café Scientifique Silicon Valley. As most of you know, we meet here on the third Thursday of every month, January through October. Next month, on July 18th, which is the third Thursday of the month, we hope to have Dr. Ron Levy from Stanford come talk to us about using immune system to treat cancer. On a personal note, I want to express my most deepest, sincere gratitude towards him. Primarily because of his research, I am not a widow today. But now, we are very privileged to have Dr. Jon Jenkins here to talk to us about Kepler and Tess. He is the co-investigator for data processing for both Kepler and Tess missions. In August of 2009, Dr. Jenkins gave a talk to this Café Scientifique audience at SRI about Kepler as it was just launched. I was in the audience then. Were any of you? Sure. Oh, very few. But anyway, we are excited that he's here again to give us an update. Dr. Jenkins joined the Kepler team in 1995 to help develop the technology for Kepler before it was selected for flight in 2002. He led the design and development of algorithms and software that are used to process the image data to search for exoplanets. When a planet orbiting a star crosses in front of the star, from our point of view, a tiny fraction of the starlight is blocked for a time during each orbit. This drop in brightness is used to determine the size of the planet and the characteristics of the orbit. This drop is so minuscule that it was difficult to believe that this approach would be practical until Kepler team did it. That is why it took 7 years from 1995 to 2002 for NASA to select Kepler for flight. In February 2014, Dr. Jenkins joined NASA Ames Research Center to lead the effort to design and build a science processing center for Tess, which is NASA's follow-on to Kepler. Tess is the acronym for Transiting Exoplanet Survey Satellite. It is performing all-sky transit survey to identify and characterize the closest and most interesting exoplanets. Dr. Jenkins holds a PhD in electrical engineering from Georgia Tech and has co-authored over 250 papers in planetary science, astrophysics, and technology. He received NASA's Exceptional Technology Achievement Medal, as well as NASA's prestigious Software of the Year Award in 2010 for his work on Kepler. But before Dr. Jenkins takes the stage, I'm gonna give you some fun facts about him. He loves to make lemon wine, roast coffee beans, and play in ukulele festivals. His 3 children are named after 3 constellations: Cassiopeia, Orion, and Delphinus. It is my honor to present Dr. Jenkins.
Thank you very much. Well, thank you very much for inviting me here. I'd like to thank Kay for inviting me specifically. And it's my great pleasure to be talking to you now, 10 years after the last time I talked to this audience, just after Kepler was launched. So I'd like to rewind the clock a little bit and think about what life was like 25 years ago, just before I joined the Kepler mission. And so this is a picture of all the known planets in the universe that we had 25 years ago. Well, a lot has happened in the last 25 years, and so we'll talk about that. So now this is a more recent picture of the planets in our universe. This is actually quite dated. It's from 2012, but it's a wonderful XKCD cartoon illustrating the state of knowledge and where our solar system fits in with all the planets that we were discovering between 1995 and 2012. So can anybody see the solar system in this picture? Okay, I'll zoom it up. And so this little rectangle has all the planets in our solar system. And besides the fact that there are almost 800 planets in this cartoon, you can see immediately that the biggest planets in our own solar system, Jupiter and Saturn, are much smaller than many of the other planets that we had been discovering up to this point in time. So if you woke up and in 2012, you would think that planets are usually much bigger than even Jupiter. We've learned a lot since then, however. So Kepler's purpose was to find Earth-sized planets in the habitable zone of sun-like stars. And so one of the questions is, how do we define habitability? Well, it means that you have to be at the right temperature. So we want to find planets that are at the right temperature so that you can have liquid water pooling on the surface of a rocky planet like Earth. Because as far as we know, the only life forms, all life forms indeed require water at some point in their development. We need air to breathe if you're going to be on the land, liquid water, light, which is the power source and drives photosynthesis, which gives us oxygen, and we need a radiation shield to protect us from mutations. And finally, we need asteroid protection. So asteroids, give and they take. We now know that comets in the early solar system formation brought most of the water to Earth after it formed. Okay, but there's also, in terms of defining the temperature of a planet, you have to talk about the distance that the planet is from its star. So in the case of Venus, it's at about 30% closer to the sun than we are, but it's uninhabitable. So it has the same bulk properties as the Earth, but it's about 800 degrees at the surface, so it's hot enough to melt lead. It's got sulfuric acid clouds, and it's got a very thick, dense atmosphere that's about 90 times the pressure that we experience here, because the carbon dioxide on Venus is in its atmosphere and not in the rocks. So we would be in the same position on Earth if we hadn't sequestered most of the carbon dioxide in the rocks below us rather than in the atmosphere. So Earth is just right. If Earth moved just a little bit closer to the sun, then we would become uninhabitable. It's on the inner edge of what we call the habitable zone. And then Mars is at the outer edge of the habitable zone as we understand it, but it's a little bit too cold, it's also too small. So you need a massive enough planet to hold on to a thick atmosphere like Earth and Venus have. So we're interested in finding planets of the right size and the right distance from their star. And of course, if you're a very bright, bigger star than the sun, a bluer star, like an A or an F star, those stars are bigger and they're hotter, and so you have to be further from a star like that in order to be in the habitable zone. Whereas a yellow star like the sun has a habitable zone similar to ours, where Earth and Mars define the borders of the habitable zone. And then if you look at smaller, cooler red dwarf stars, then they're smaller and they're not as hot, and so the habitable zone is much closer to them. In fact, the habitable zone for the smallest stars are on the order of tens of days, maybe like 20 days for the habitable zone. Well, how do we find these planets? Well, how many of you saw the transits of Venus in either 2012 or 2004? I hope many of you did. Okay, so that was your opportunity to see an Earth-sized planet cross the face of a sun-sized star. And this is something very similar to what you would have seen if you were lucky enough to be in the right place to be able to observe the transits of Venus on either of those occasions. But of course, we're much further away from the stars that we want to observe than we are to our own sun. And so we can't resolve the disk of a star at this distance, so we can't see the silhouette of the planet. But we can measure the shadow. And so how Kepler works is that we observe a field of view of 150,000 stars, and we watch for instances where the planet does indeed cross the face of its star from our point of view. We can't see that, but we can measure the light from the star, measure the brightness over time, and look for dips that last from typically an hour. If you're in a very tight orbit, say 3-day period orbit, you'll have a transit that lasts about an hour. out to about half a day. So if we were somewhere else in the universe looking at the Earth crossing in front of the sun and Earth crossed the very center, the middle, then the transit would last 13 hours. On average, we expect it to be about 10 hours, though, because of just random inclinations. So that sets the time scale for finding these planets. You never know when a star is going to wink at you. You never know when a planetary transit is going to happen. So you need to be observing as continuously as possible. So that's one main reason why we needed Kepler to go to space, and we couldn't do it from the ground. You can imagine trying to do this from the ground, but there are several things that impede you, that get in your way. One is the fact you can only observe the stars at night. And the other is that you've got weather. And so even if you could observe every night, not every night is going to be good enough in terms of allowing you to see the stars well enough. And the other issue is that you can't reach the level of precision that you need to find these small planets. So 25 years ago, it took professional astronomers to find Jupiter-sized planets like this. So here's the silhouette of Jupiter on a sun-sized star. Jupiter is about 1/10 the size of our sun by radius. And so that means that when it crosses the face of our sun, it causes a 1% drop in brightness. And so indeed, here's a Kepler planet that's about 10 Earth radii, so just a little bit smaller than Jupiter. And you can easily see in the Kepler data the drop in brightness caused by this planet crossing the face of its star. And it has this very typical U shape because stars are not uniformly bright across their disk. They're darker at the edges, so that's why you have a U shape. Earth, by contrast, is 10 times smaller than Jupiter. So that means rather than causing a 1% drop in brightness, it causes a 1 part in 10,000 drop in brightness, a percent of a percent. And that's too small a change in brightness for us to be able to measure that from the ground because of the atmosphere. So everybody looks up at night and everybody knows that the stars twinkle, and it twinkles because of transparency variations and density variations in the atmosphere so that the light gets scattered and you see the stars twinkle. So that twinkling is too big for us to be able to measure these very small changes in brightness corresponding to Earth-sized planets crossing other stars, except in very special circumstances. If you look at the very smallest stars, then you can detect them from the ground in those instances, and so we've seen some of that happen. But Kepler wanted to find planets around sun-like stars, and so we launched in March of 2009 on this Delta II. It was the next to last launch of Delta IIs ever. And a month later, we opened up our dust cover and we took this image. So we have 42 charge-coupled devices. These are image sensing chips similar to the ones that you have in your iPhones, your phones, or your digital camera, except that they're 1 inch by 2 inches wide. So these are bigger formats than most people are used to. Our field of view is really big. So this is the full moon. It can fit inside the gaps in between the modules that hold our image sensors. And for reference, if you hold your arm out at arm's length and look at the palm of your hand, that's about the size of this field of view. Compared to Hubble's field of view is about the size of a grain of sand held at arm's length. So these two missions are really phenomenal, and they've been extremely productive, but they have very different objectives. So Hubble wants to look very deep, and it needs a lot of spatial resolution. You want to look at things that are really tiny on the sky because they're far away. Kepler wants to look as broad as possible because we want to look at lots of stars simultaneously. Well, we did launch. We had a launch party, so that's what I looked like 10 years ago. And we had a lot of public interest in our mission along the way, and Lieutenant Uhura visited us, and we're all Star Trek fans. She found a phaser on our conference table, and good thing that that was on stun because she was waving it around and shooting people with it. A lot of fun. So what did Kepler discover? So here we are. Kepler actually was retired and turned off last October after running out of fuel after nearly 10 years of observations. And we actually had 2 missions. We had the primary mission where we observed over 100,000 stars continuously for almost exactly 4 years. Over the course of the 10 years, we observed over 500,000 stars. We have confirmed over 2,700 planets. This is a little dated, so we're still finding planets in the Kepler and the K2 data. And we documented over 60 supernova. This is something that Kepler was not designed to do well at all, but we managed to find over 60 of them. So we collected about 1 terabyte of data. And then one of the most important things for scientists is that this is an extremely productive mission. We published over 3,000 papers coming out of Kepler. And that's actually phenomenal. That puts us in direct competition with Hubble in terms of the productivity of this mission. We're about 95 million miles away now, and we managed to go that far on just 3 gallons of fuel. Actually, that's a little bit tongue-in-cheek, because we launched on the Delta II, and the Delta II basically kicked us out hard enough so that we wouldn't come back and smack the Earth. And so we're actually in an Earth-trailing orbit that's 1 week longer than Earth's orbital period. And so eventually Earth will lap us, just like Venus laps the Earth in its orbit because it's in a tighter orbit. Okay, so this shows planet discoveries over time. So this is the size of the planet. So here's Earth. This is orbital period. This is 1 year. And you see that first we were discovering planets through radial velocity, through the Doppler reflex motion of planets tugging gravitationally on their star and making it wiggle. But then in 2000, we discovered the first transiting planet, and the ground-based transit surveys are really good at finding Jupiter-sized planets. And then the red you see there are the Kepler discoveries. So Kepler has discovered over 2,700 planets. Other transit surveys have discovered about 400. Radial velocity planet discoveries account for about 800, which this was the first method that was used, and it still provides a lot of information. In fact, it's the best of both worlds if you can find a planet that is transiting, for which you can also measure the mass directly. That gives you the best science. We also have about 40 planets that have been discovered by direct imaging. These are mostly very large planets that are very far from their star. That's going to get better as time goes on. We build better instruments. We'll be able to move our sensitivity inwards towards the star and directly image smaller planets closer to their stars. And then we have gravitational microlensing, which has detected 75 planets. Now, back in 1995, when I joined the Kepler team, I attended a conference called Exploring Nearby Planetary Systems, hosted by JPL, where they conducted a study that lasted about a year, at the conclusion of which they determined that transit photometry would never work for finding Earth-sized planets. In fact, they concluded that gravitational microlensing was the way to go, that would pave the way to find Earth-mass planets in the galaxy. But you can see that although microlensing, I'm a big fan of gravitational microlensing, the promise that was held out for gravitational microlensing did not come to pass, because you actually need a second observatory in order to really pin down the masses of the planets you find through gravitational microlensing. And so that's going to be the subject of the WFIRST mission that's going to be launching later on. Okay, and then we have the Tess mission, which just got underway a year ago in terms of the science data, and we have 20 confirmed planets. So altogether, we have 4,000 planets and counting that have been discovered in the last 25 years. Okay, so some of the important firsts for Kepler were, here's Kepler 20e and 20f. These are the first Earth-sized planets that were ever discovered. And we see here basically the light curve, or the measurements of brightness over time for this star. And if you see the little lines hanging down, those are the transits of the multiple planets that are around this star. The other thing you can see is the bigger wiggles. Those are caused by stellar variability, by star spots that are rotating in and out of view as the sun rotates, as the star rotates. And the interesting thing is, although that's a noise source for us, it's also an information source. So you can, if you know the color of the star and you know the rotation period of the star, you can estimate the age of the star and hence the age of the planet. So it's a really good thing that we can see the spot modulation here, because that helps us learn more about the planet and about the star. And let's see if this works. I made a sound file so you can hear what this data sound like. So if you hear the rapid da-da-da-da-da-da-da-da, those are the transits of the planets. Okay, another first. So we discovered Tatooine, or at least a planet very similar to Tatooine. So Kepler 16b was the first planet discovered, about a Saturn-sized planet discovered orbiting 2 stars, not just 1 star. Now the interesting thing is that I started working in exoplanets back in 1994 with an international collaboration of scientists who wanted to find planets transiting the smallest known eclipsing binary at the time, CM Draconis. We observed for 6 years, but of course we never got any funding. We made lots of proposals to NASA and lots of proposals to NSF, but we never were funded. Why? Because when you submit a proposal and you get turned down, they actually tell you why you were turned down. Here are some of the reasons why we were turned down. Planets don't form around M stars, red dwarfs, so that was one of the things we were told. And indeed, one of the stars that Kepler 16 was discovered around is an M dwarf. The other thing we were told was that planets can't form around binary stars. So it's amazing that the reasons why we were turned down were things that nobody had any idea about. So it's interesting. Theorists can tell you something can't happen. As soon as you discover it, then they can come up with a theory in a few days for explaining why it actually exists. In fact, we've discovered about 10 or 12 systems like this, and I think in the first 3 or 4 we discovered Kepler 47, which has a planet in the habitable zone of its binary pair of stars. Let me tell you, it took a lot more than 6 planets to be discovered before we discovered the first planet in the habitable zone of any star when we're talking about single stars. Okay, so another phenomenal thing we learned from the Kepler mission, and this took a lot of time actually, was if you look at a histogram, so these are the number of planets per 100 stars, and this is the size relative to Earth. And so we see that the frequency of planets rises as you go from Neptune size, 4 Earth radii, down to about 2.2 Earth radii. And then you see this gap, and then you see another peak here below about 1.6 Earth radii. And so Kepler 22b was one of the first planets that was discovered in the habitable zone of its star, but it's about 2.4 Earth radii, and it's too big for it to be rocky. So it must have a large convective envelope of hydrogen and helium, and it may have a large abundance of water. Kepler 452b is right now is the best or the truest, closest thing we have to a true Earth-Sun analog. So it's a planet that's in a 385-day period orbit about its sun, and its star is very similar to the sun. It's a little bit older, but it's effectively the same temperature, color as the sun, and it's right on the inner edge of the habitable zone for that star. We now know, after many years of doing a much better job of understanding the properties of the stars that we've observed, that these super-Earths that are between 1 and 3 Earth radii fall into 2 camps. So there are 2 kinds of planets that we're talking about. They're planets that are most likely to be rocky and have very thin atmospheres, relatively speaking. And then there are the planets that are more like mini Neptunes. So we think the planets are sorting themselves into 2 basic kind of planets when you're talking about sizes between 1 and 4 Earth radii. So this is something we had no idea about 25 years ago. All right, the other thing is that Kepler was an asteroseismology machine. It turns out that stars are resonant cavities. They ring like bells, and they have starquakes on the surface. And what this little video is illustrating is the fact that sound waves that are created at the surface then go interior, then get refracted back up to the surface, get reflected off the surface, and travel around, kind of like a daisy chain. If they end up at the same place that they started, it keeps on going around. So you can set up quasi-coherent oscillations of these sound waves. And the nice thing about this is that just like bells, if you measure the tone or the frequency of the oscillations, you can predict the size and the mass of the bell. In fact, we can measure the size and the masses of these stars to about 2%, which is really amazing because you can't resolve the size of the star. You're just measuring the changes in the brightness of the star caused by the fact that the star's shape is changing just a little bit. So this is a panel of 9 stars. Temperature is increasing to the left. luminosity or size of the star is increasing towards the top, and frequency is on the x-axis. And if you look closely, you can see for the coolest, smallest star here, it's got coherent acoustic oscillations between 3 and 4 millihertz. As the stars get hotter, the frequency of these oscillations moves lower in frequency to about 2 millihertz in this case. And then as we move up to bigger and bigger stars, the frequency gets lower and lower, right? Just like the bass, profundo basses sing very deep and the sopranos sing very high. So you can actually make an orchestra of stars. So the one of the funnest things about Kepler is it's inspired lots of artists and musicians. So this is an installation that a Austrian artist did in collaboration with one of our scientists who extracted the acoustic oscillations from hundreds of stars and then created this, hope that goes. But in the meantime, I'll also tell you about this. So after 4 years of collecting data from Kepler, we were able to measure the acoustic oscillations of over 15,000 stars. Now this is showing the luminosity or brightness, and this is the effective temperature or color of the star. These are very low amplitude oscillations for main sequence stars that are still burning hydrogen, whereas these stars up here are exhibiting much larger amplitudes in their acoustic oscillations because they're giant stars. And the amazing thing about this is that this inset shows you the stars that we were able to measure these pressure mode or acoustic oscillations before we launched Kepler, and there were only about between a dozen and 20 such stars. Okay. All right, so one of the other exciting things we got out of Kepler was the fact that we observed over 60 supernovae, and this one, Kepler Supernova 2011d, is very special because we actually saw the shock breakout that happens at the very beginning of some of these supernovae, and you can see it in the inset. It's a very sharp increase in the brightness from a level of 20,000 to about 130 million. So that's a very large increase in the brightness. And that's what happens when you get the shock wave that goes out and shocks the material. So you get this flash, but then it dies off, and then you have the expansion of the system that takes place over a much longer time frame that causes the much larger increase in brightness over time. But the fact is, if you're looking for supernova, you aren't looking at the whole sky all the time continuously, so you generally find them after the shock breakout has happened. So this was the first measurement of the shock breakout in the visible anywhere. So it helps point us towards clues as to what the progenitors are for supernova, what kinds of stars are actually combining to make the supernova happen. Another fascinating discovery was one we had no idea would be out there to find, was Kepler 12557548b. It's called that. It doesn't have a Kepler number. It got a Kepler number later, actually, because it was so weird. And that is, we were looking at this light curve, and every 16 hours we could see a transit happening. There were some times when it didn't happen at all, but it changed its depth over time. Well, if you have a solid planet crossing in front of a star every 16 hours, you expect to see the same depth of the transit every time, the same amount of brightness taken away. But instead we see it changing. And so our best guess, which is no longer a guess, we've determined that this is caused by a planet that's actually disintegrating. It's being evaporated by its star over time. And the fact is, the star has spots, and that means that the amount of material that's being blown off the planet changes over time. It condenses and forms a comma-like tail, and so the density and size of that tail is changing over time because the planet is seeing different amounts of light from the star, which heats it differentially over time. This is very rare. This star is a K star. It's hot enough to do this job, to evaporate this planet, but it's cool enough so it takes a long enough time for us to be able to see it. It's still very rare. We think it only takes about 1 million years for this to be over and done with. Yes? There are models that were fit to the signatures, and so I can't remember the numbers offhand, but they do estimate the winds and the amount of material that's being blown off the planet over time. Oh, you're talking about the supernova. Yes, scientists who know about that can do that. Yes. All right, so we only had one or two at most other candidates that were in this case of disintegrating planets. So it is a very rare thing to be able to see. The other thing that came out well after the mission was over, the primary mission, was discovery of exocomets around 2 different stars. Now these were 6 exocomet signatures in visible light around one particular star. And the shape, right now we call this a candidate, but this is our best idea of what's going on, that you have comets orbiting the star and crossing in front of it, causing these transit-like features that have sharp ingresses and relatively gentle egresses. And this represents the first time that we've seen signatures of comets in visible light around another system. We have some other weird, wacky stars, like our Alera stars. These are stars that oscillate, they pulsate radially, kind of like a pot of boiling water on a stove with a lid on it. So there's an atmospheric layer that's normally opaque, and that traps light and heat inside. It gets to a point where it ionizes and becomes transparent, and the star every 12 hours then has this very sharp increase in brightness. But then that lets the heat escape, so that layer cools down and becomes opaque again. So you get this oscillation over time. And if you play this light curve as a sound file, this is what you hear. The other thing you'll notice is that the amplitude changes over time. That's known as the Blaschko effect, and that was discovered by an astronomer who happened to be named Blaschko over 100 years ago. The other thing we didn't know what it was when we first saw it was that we saw this star that increased its brightness every 42 or 43 days. Very sharp, very repeatable. So this is, if you take the full light curve here and you fold it at its period, you see this signature. You see all these oscillations. This happens to be a pair of stars that are nearly the same, but they're in a highly elliptical orbit about one another, and they don't cross in front of each other. We've seen dozens of cases like this, some of which do have the stars actually eclipsing one another. You can see little eclipses, but you don't see them here. The stars get so close together that they actually gravitationally pull each other's shape out from being a sphere, so they become gumdrop shaped, or more like an American football shape. And it's just like with the acoustic oscillations. If you have something that's shaped, that's elongated, and it rotates from here to here, now it's presenting more cross-sectional area, and so you get more light directed towards you. So that's what's happening here when the stars have this close passage. They draw each other out, so now you see a lot more cross-sectional area on the sky. But they're also perturbing each other, like hitting each other with a hammer, like a bell, and so they oscillate, their shapes oscillate, and they're oscillating at the 91st and 92nd harmonic of the orbital period, which is why you see all these little oscillations. And this is what it sounds like. There you go. Okay. The other thing we had no idea that we would discover was multiple transiting planet systems. So if you pretend like we did when we were forming this mission, that all the planet systems we would discover would look like our own, you would expect that in about 12% of the cases, when you found a planet like Earth, you would find a planet like Venus. So we expected that, yeah, we'd have a couple of multiple transiting planet systems, but what we found was totally different. We found over 500 multiple transiting planet systems, and so here what you're seeing is a visualization of what these systems look like from the top down. And if you look closely, you can see that the planet size is scaled against the other planet sizes, and the orbital sizes are scaled versus orbital sizes, but the two are on 2 different scales. At any rate, it's just one of the biggest surprises out of the mission was to find so many compact planetary systems with 2, 3, 4, as many as 8 planets in them. And so what this means is that our general idea of how planetary systems form from a collapsing protoplanetary into a protoplanetary disk from a nebula is right. As the cloud collapses, it tends to collapse into a plane, and it tends to spin up, and you have the central portion collapsing to form the star, and you have then clumps forming and planets forming in the outer regions of the disk. And then when you have the star actually begin to shine, it blows away the dust and the gas, and you're left with the planetary system that you see, but you can have scattering events that change the morphology or the architecture of the system. But really fascinating because we had no idea there were so many planets to find. Yes? Mm-hmm. Right, so there are two questions. One is, do you expect the planets to form in the ecliptic? And around the star, yes, we expect that in most cases, the spin axis of the star is coincident with the orbital axes of the planets. And in fact, we know now that these systems that we've discovered have dispersions in the inclination angles of the orbits of a couple percent, which is very similar to what we see in our own solar system. Now you can have scattering events where you have big planets that move around in the system. We know that that's happened in our own solar system, and they can shepherd the planets in. In fact, we think that's happened in many of these cases because these systems are dynamically packed. If you tried to move the planets closer to the star or to one another, they would become dynamically unstable and we wouldn't see them at all because they would have destroyed themselves. The other question that you had was on, excuse me, go back to it. Right, yes. Yeah, so that's why we had to look at least 100,000 stars, because if you're looking at the Earth and the Sun from somewhere randomly on the sky, you only have 0.5% probability that you would actually see the Earth cross the Sun's disk from your point of view. So that means for every Earth-Sun analog system we find, there are 200 out there that we couldn't see with Kepler because you don't see the transits. The planet is always outside of the disk of the star. Okay, so why am I here? And why was Kepler a success? Well, at least in one small but important part, we needed to be able to process all the data coming down to look for these very weak signatures. It is a very difficult measurement to make. There are all kinds of things that are fighting you. We've got the stellar variability of the stars themselves, star spots, flares, other kinds of things going on. But we also have the instrument. The instrument isn't perfect. There are all kinds of instrumental effects that make it difficult to find the planets that we're trying to find. So we had to build this data processing facility, and we had to design and develop algorithms that allowed us to reach the sensitivity that we needed to find all these planets. So I won't go into the details, but we ended up writing about 1 million lines of code. We had 26 different modules that we needed to build in order to do this job. We did develop a very flexible pipeline control system that can be run on a laptop, on a workstation, on a computer cluster, or indeed on the supercomputer at NASA Ames Research Center. And it turns out that finding this needle in a haystack is very computationally intensive, so we needed to have a lot of computational power to do it. Yeah, so the search problem is very much like searching for a needle in a haystack. You never know when the transit's going to occur. Stars have other kinds of phenomena that cause dips, so you want to be quite certain of what you're finding. And of course, we're getting a bale of data coming down on our heads every month with Kepler, and that's not all you get. Every month you get another bale of hay coming down on you, and so you need to be able to learn as much as you can about this instrument and about the spacecraft and about the sky, about the stars, because nobody had ever done this before. We never had an instrument with this level of photometric precision that we could collect this kind of data with. So it was very much a bootstrapping process of learning as we were doing in order to make this work. But it became readily apparent that we needed to increase our computational power in order to keep up with the data. So Kepler very much found itself falling over the waterfall in terms of being inundated with all this data and not being able to deal with it. We could keep up with the data, but with our original system, which is pictured here, this was the hardware that we bought and installed. We had about 700 CPUs, about 4 terabytes of RAM, about 300 terabytes of raw disk storage. 2 years into the mission, we believed that we had learned enough about the instrument, enough about the sky that we wanted to reprocess all that data because we could find smaller planets that way. It took us 10 months to process 2 years of data. And we knew then that we were going to have to do that many times over. So we had to do something different. So we moved our operations in terms of our number crunching over to the NASA Pleiades supercomputer that's at Ames. It has over 250,000 CPUs and about a petabyte of memory and 29 petabytes of storage. And so this is just one aisle in this huge warehouse full of all these computers. In fact, we can't add any more computers to the NASA Pleiades facility because the floors would actually collapse under all the weight. And so we're building these outriggers now that are in different locations on campus that actually are phenomenal because they're going to be air-cooled, which is much more environmentally friendly because we use an awful lot of the power not for the electronics, but to cool the electronics. So we have huge operational costs for the supercomputer with respect to the AC and also to the fact that we've got a water-cooled system. So, so we're moving into the new century with better technology. This shot on the right here is actually the NASA Pleiades hyperwall, and we're showing results from the transit search happening in real time. So after moving our operations over to the supercomputer, it took us only a couple months to process 4 years of data rather than 20 months as it would have taken with our original system. Okay, so planets are everywhere. Kepler now has shown us that every single star you look at has on average one planet. And if you find at least one planet, typically you're going to find more than one planet.
That was the question.
Okay. All right, so yeah, so Kepler's dead now. Long live Kepler. But we've got a new mission called the Transient Exoplanet Survey Satellite. So this is a mission that never would have been selected had Kepler not launched and been successful. But its goal is to find new Earths and super Earths in the solar neighborhood. It launched in April of 2018, so just a little bit over a year ago. It was on a Falcon 9, launched for us by SpaceX. And yes, they did stick the landing with the booster. And this illustration shows the key differences between Kepler and Tess. So Kepler, here's the sun. Kepler was looking along the Orion arm of the Milky Way galaxy in a 100 square degree field of view. And we are looking between typically 1,000 light years and 3,000 light years away for the typical distances for the target stars that we were looking at during the Kepler mission. Tess, now with the knowledge that almost every star has at least one planet, is looking at stars in a near all-sky survey that are typically 10 times closer. So it's concentrating on especially the red dwarfs, the M stars, out to about 200 light years. But the stars we're observing are typically 10 times closer and therefore 100 times brighter than the stars that we observe Kepler. And that's very important because although we found 2,700 plus planets with Kepler, most of them are orbiting stars that are too dim for us to do much follow-up or characterization on. So we can't directly measure the masses or even indirectly infer the masses of most of the planets we found with Kepler. So we know the size of the planet, but that turns out to not be a very good indicator of what the planet is made of. Yes?
What's a nebula?
What's a nebula? A nebula is essentially a cloud of dust and gas, and we often have star-forming regions in nebula. Right, so how does Tess do this? Well, Tess has 4 cameras, each of which has a 24 by 24 degree field of view. So that means that we're seeing about 5 times the area on one camera that we saw with Kepler. And the field of view stretches 24 degrees by 96 degrees. So that's huge. I mean, I told you that Kepler's field of view is huge. It was until recently, and now people say that Kepler's field of view is small. We were talking about astronomical telescopes. That's not true. but Tess has just a huge field of view compared to anything else that we have going. So we observe a strip of the sky, and then every month we turn and we look at the next strip of the sky, and we do that 13 times, and then we map out one hemisphere of the sky. The cool thing is that we've got one camera that points at the celestial pole, and we just rotate around that camera so that we have over 500 square degrees that are pointed at the same location on the sky for a single year, for a full year. We have 2 years in the mission. For the primary mission, the first year we're mapping the southern hemisphere. You can see here, this is a little bit old, but this shows you a mosaic of our full frame images that came down over the first 8 months of observation. We've gotten the 12 months of data down, 12 sectors, and we're going into our 12th month, which will fill in the last little sliver over the next month. Yes?
How many stars are there in this region?
Oh gosh. In terms of things that we're going to observe over 500,000 stars over the 2 years, but there are many millions of stars that are in the field of view. And it depends a lot on where you're looking. So there are times when we have the Milky Way in our field of view, and so you have a huge number of stars there. So it's a very new mission. We're about a year into it, but we already have some very exciting results. And so we've got about 700 planet candidates. This actually is about a month old now. We have 20 confirmed planets in the literature. We have, back about a month ago, we had 137 publications. I know now that the Tess team itself has 42 publications that have either been published or in the works. About half of them are on exoplanets, about half are on other astrophysics topics. We're looking at a much broader diversity of stars than we were able to look at with Kepler. And so there's a lot more astrophysics that you can do with the Tess data. One of the systems that we've found and published is a 3-planet system called L9859. It's got planetary radii between 80% and about 60% more, bigger than the Earth. And we've got direct mass measurements from HARPS, which is very important because if you have the mass and you have the size of the planet, then you know what the density of the planet is, and then you can start arguing over what it's made of in earnest. And this is an exciting system for potential atmospheric characterization with Hubble Space Telescope and with the James Webb Space Telescope when it launches. So we actually we've downloaded almost all the data from Sector 12. We've got a few full-frame images that we need to download at the next opportunity, but we're already processing Sector 12 data as of this week. I want to tell you a little bit more about this image. Right, so this is a mass radius diagram. So we have planetary mass on the bottom from about 60% of the mass of Earth. Here's Earth right there, out to 20 Earth masses, and then we've got the size of the planet on the y-axis. Again, here's where Earth is, right there. Here's Venus, and then it goes up to 3 Earth radii. And so what you'll note on this diagram is that we have 22 planets, and we had on the order of 1, 2, 3, 4, so about 10 of these planets are Kepler planets. Out of the 2,700 that we discovered, we have about a dozen or fewer for which we've got both mass and radius measurements. So although Kepler has taught us that planets are ubiquitous, they're everywhere, we really need to know not just the radii of the planets, but we need to know what their masses are in order to start talking about what they're made of. So if you look at these curves show you how the radius would change as you add mass to a planet with a given composition. So this top curve is for 100% water. So if you had planets that were 100% water, they would fall on this curve. And you indeed see that there are some planets out here at very high radii and with very high masses that look like they might be consistent with being mostly water. At the very bottom, if you have a stripped iron core, then you would have very dense planets, so with much smaller radii as a function of mass. And you see that magnesium silicate, so here's this curve here, shows you what an Earth composition-like planet would be in terms of its radius as a function of the mass. And you see Earth and Venus lie very close to that curve, and you see that L9859c, so the second planet discovered in this system, lies right on that line, along with a collection of other planets. So we're starting to see this region fill in. And then we have this clump up here of planets that are not Earth-like in their composition. And then we have the third and smallest planet here, in the shortest period orbit. We've only got an upper measurement of the mass at 1 Earth masses. It's likely somewhat interior, so it may be fully consistent with being a stripped iron core. So this is really exciting. We have a number of other discoveries that are under review right now. But right out of the gates, we're starting to fill in the mass radius diagram. This is where the science really happens. But that's not all that we can do with Tess. I'll come back to planets in a little bit. So we also, with Tess, even though it's been up there for about a year, we've already identified over 50 supernovae in the first 9 sectors of observation. So in the first 8 or so months, we have almost as many supernovae as Kepler was able to see in 10 years. And the reason for that is that Kepler actually could not download all of the data. So we observed, we had a 95 megapixel camera on Kepler, but we can only afford to bring down the postage stamps of the stars we were interested in. And so we only brought down about 6 million pixels out of the 95 million pixels that were available to us because we couldn't store all that data and we couldn't download it all either. So it's kind of like taking your high school yearbook and cutting out the pictures of your friends and pasting them on a new page and then ripping the page out and throwing the rest of it away. So there was a lot of science, unfortunately, that we could have done with that data, but we just could not, didn't have the technology available at the time to store all that data. Well, Tess is a lot newer, and it's also in a much different orbit. Tess is in a high Earth orbit. What it means is that when it's at its closest approach to Earth, when we downlink the data, it's only 17 Earth radii away. It's not halfway around the sun. So we've got a much bigger pipe that we can download the data through. It also has about over 15 times as much data storage on it. So most of you probably, if you looked at your computer system you had 10 years ago, you had a lot less data storage than you do today if you buy a new one. Well, the same thing happens on spacecraft as well. So what that means is that we can collect half-hour full-frame images. So this is the same cadence as we had for the 150,000 stars on Kepler, which we observed and sampled every half hour. We can do that for 1/26th of the sky all the time as we're observing. So this is going to be a phenomenal science treasure trove for many years to come, because you can do all kinds of science on stars in the full frame images that you don't even know about today. And in fact, we have several different groups that are observing our fields of view while we're observing them, and they're alerting on supernova. And so they know that when we bring the data down a week later or so, that the supernova will have been observed in the test data already. And so this is proving to be very fruitful. We've observed 53 so far, and we believe that after 3 years of observations that we'll have at least 200 such supernovae. And we're hoping also that we'll be able to do multi-messenger astronomy and actually observe optical counterparts to gravitational wave discoveries by LIGO. And that's going to be very exciting when that happens. But coming back to planets and why are we doing Tess in the first place? Well, Tess is kind of like a finder scope. The science is only beginning at the end of the Tess mission. So we're finding these small planets, we're measuring their masses, we're starting to argue over what they're made of, but what we really need to do is we need to follow up and characterize them with bigger missions like James Webb and WFIRST and succeeding missions that have much larger apertures and much better technology than what we have today. And ultimately what we want to do is we want to look at the spectrum of the light that's either being transmitted through the atmosphere of the planet when it's transiting a star, or what we really want to do eventually is we want to look at the reflected light spectrum. We want to block the light from the star, and we want to look at the spectrum, or the distribution of the light with color that's being reflected off the planet's surface. And the reason why we want to do that is we want to study, you want to see day-night cycles as the planet is rotating. You want to look at the climate or the seasons of what's going on. You might be able to detect changes in the emitted light that reflect the growing seasons. And you also want to look for direct evidence of molecules in the atmospheres of these planets that are associated with life. So we want to look for ozone and oxygen because, hey, we all breathe oxygen. We want to look for water vapor as a tracer for water, carbon dioxide, and methane, and some other interesting molecules as well. But the great thing about detecting a lot of methane and a lot of oxygen is that those two chemicals like to react. And so if you're in chemical equilibrium, you don't have a lot of both of these chemicals. You either have oxygen and almost no methane, or you have methane and almost no oxygen. Because as you all know, methane burns, right? It likes to burn a lot. So we have a significant amount of methane and oxygen in our atmosphere, but the reason why it's there is because we have life that's driving our system out of chemical equilibrium. And so we believe that if you find significant abundances of methane and oxygen, that's a strong indicator of life on that planet. So that's something that we can't do today, but we hope to do in the years and the decades to come. And so NASA does have a whole slate of missions whose primary purpose is to determine whether or not we're alone, to look and search for signs of life in the universe, biological activity. And so we have Hubble playing a role, Spitzer, which followed up a lot of the Kepler discoveries, Kepler itself, Tess, which is on orbit now, James Webb, which is inching closer and closer to launch. And so it'll be really a fantastic thing when James Webb gets up there, because in a couple of years, we'll have lots of targets for James Webb to look at and characterize. WFIRST is a mission that's in formulation right now. That has a strong exoplanet component to it. And then New Worlds Telescope, there are 3 competing architectures for this mission concept that would be capable of following up and characterizing planets well beyond what we can do with James Webb Space Telescope or WFIRST. So 25 years ago, you were a strange character if you believed that you could find planets elsewhere in the galaxy. That was something that put you on the fringe. Bill Barucki, the principal investigator for Kepler, started this work in 1984, and almost everybody thought that it could never be done, that it was impossible. It took him a couple of decades to accumulate a science team and to convince our colleagues that this was something that we could do. So today we look at Kepler and we say, oh my gosh, what a wonderful success it is. And of course, why would anybody believe that it wouldn't have been a success? But 20 years ago, people were very skeptical, and it took a lot of time and effort to convince people it was worth doing. Today, Kepler's just blown open the door and allowed these other missions to be selected, flown, and conceived of in the first place. And NASA is not the only entity that's doing this too. ESA, the European Space Agency, also has several exoplanet missions that are either about to launch or on the drawing boards for launch later. So something that was impossible 20 years ago now is a burgeoning, very large and active field of inquiry. And we can look forward to many years and decades of exoplanet science and other science to come. So at this point in time, I'm ready to take your questions. Thank you.